So we're going to do the parallel set for piecewise reduction. And, I hate doing the parallel set because it's so disingenuous. I'm thinking maybe if this class is feeling extra smart, we can just jump into a real one and do a real one. How do you guys feel about that? Or do you want me to just do the plain old one that's easy? Okay. Let's do what I did in every other class. Maybe Mr. Shelton's just getting bored. That could be it. So a simple parallel circuit, like so. I am going to change one thing because I do need to highlight some of the issues. So what I'm going to change is I'm going to make this 3 ohms and not 2 ohms like yesterday. I'm still going to say that this is 6 volts. Now, this circuit, through piecewise reduction, can be reduced by using the rules of parallel. And the rules of parallel are similar to, but different than, the rules for series, in that there is an equation that will tell us the equivalent resistance, that will take this circuit and reduce it to a circuit that has 1 equivalent resistance to replace the 2 that are in parallel. And when I do that, I'm looking to find what the equivalent resistance is. Now, the relationship is a little different. And it doesn't give me R, it gives me the inverse of R. Now, to understand this, you have to understand that the equivalent resistance for parallel will have less resistance. There's more pathways for the charged particles to go, so there's less total resistance. So our answer is always going to be an amount of resistance that is less than was there before. The way it works is you add up the reciprocals to get the equivalence. Now, this isn't particularly hard. I have 2 3-ohm resistors. So to figure out the equivalent resistance, which I'm putting R with, these 2 lines aren't 11. I'm putting R with 2 parallel lines next to it. So it's R parallel. That okay? It's easier than writing parallel, which I can never remember if it has 2 R's or 2 L's. That's going to equal 1 over 3 plus 1 over 3, which is not 2 over 6, although some of you think it is. It's also not 1 over 9, which some of you think it is. Look, you're going to have to add fractions in this class. And should you do something like this, I promise to hang yours up on the bulletin board and call attention to it. And I won't warn you ahead of time. You'll just notice me stand up in the middle of next week's pop quiz and staple a piece of paper to the board. That's your quiz, because you can't add fractions together. And yes, we are all making fun of you. Does everybody understand? Have I given you fair warning of what I'm going to exploit on Monday or Tuesday of next week? Good. Because we know, because we passed the 3rd grade, that when you want to add fractions together, you must get a common denominator first, which I already have. And because I have a common denominator, I merely add the top together and get 2 over 3. Which is why the resistance is 3/2. The other mistake you're going to make is R doesn't equal 2/3. 1 over R equals 2/3. So R equals the reciprocal, 3/2. Do you understand the other mistake you're going to make? This one I won't exploit for sport. I will just say it's heartbreaking when you don't do this. You guys understand? It's such a little tiny thing. Is any one of these things hard to do? But you understand that that's just one itty-bitty step in the grand scheme of all of this. So although this is not hard, the math is easy, the process is easy. You get busy, you get not thinking, you think, wow, this is super easy, and all of a sudden, you get that. So that's why you need to be careful. Please take your time and make sure you know how to add fractions together. Now, 3/2 is also 1.5 ohms. I tend to work in fractions. You guys tend to like decimals. Whatever. Now, once I get to this point, I'll remind you that your actual goal is to find the voltage and the current for the objects in our circuit. So we have 6 volts applied to this circuit. I don't want to spend a lot of time reminding you of stuff from yesterday, but Ohm's law is current equals voltage divided by resistance, and power equals voltage times current. I know that's all in your notes, and that's the last time I'm going to remind you. But 6 divided by 1.5 is 4 amps. I'm not going to worry about the power right now, because once I have voltage and current, I can get the power at any time. Getting voltage and current is the most important part. But now I want to step back and go back to where I was. Now, when I step back, just a reminder, yesterday we went back to a series circuit. We took the current and applied it to each element in series. For parallel, we apply the voltage. So when I step back, there's 6 volts applied to each of these elements in parallel. Now, I really didn't have to do this circuit in front of you. Look, both of those resistors were connected to the 6 volts. You can see it in the picture that this 6 volts is connected right to here and here, which is why we could have skipped this one. But I want to show you how this process is done. At this point, I use Ohm's law again to figure out what the current is. 6 divided by 3, 2 amps. 6 divided by 3, 2 amps. And of course, 2 amps plus 2 amps equals 4 amps. You can always check your work. Now, the last step is to figure out the power. We should probably do that real quick just to make sure you can. Figuring out the power, 2 times 6, 12 watts for the first bulb, and 12 watts for the second bulb, for a total power of 24 watts. Go back to my reduced circuit, 4 times 6, 24 watts. There will be multiple ways to check your work. I would save power as a final check at the end and use voltage and current for checks between steps. Okay? Now, that you guys can actually do something with this information. Now, the first thing I'm going to do is I'm going to kind of screw with you a little bit. One of the things that's hard about this is knowing how your circuit elements are arranged. We are looking for instances where there are resistors in a row, or there's a clear set of resistors that are side by side. I put 3 here to remind you that it doesn't matter whether you have 1 or 2 resistors in series or 100 series in resistors in series. It's still going to be the same reduction. You add them up. I don't want you to get fixated that things have to be 2 or 2. They don't. But I don't want to also make this overly complicated by just putting 4 of them in a row just so you can add up 4 numbers. So you need to look for parts of your circuit that are clearly series or clearly parallel. The problem is that this circuit, it might not be clear to you. It's sometimes easier to redraw your circuit so that you can kind of help identify what's in series with what. And what I mean by that is to take your circuit and put all of the resistors between here and here. To draw it in such a way that it's easy to see what's in parallel and what's in series. To do that, I'm going to take the circuit we have here and I'm going to redraw it over there. And I'm going to kind of talk you through my thought process. First, starting at the battery all the way to here, that X and that X represent the same point in the circuit. So over on the original circuit, I must pass through a resistor before I get to this place where the current separates. So pass through a resistor until I get to a point where the current separates. A separation in current I'm going to draw as a horizontal line. Next, I got to pick a side. So I'm going to pick this side first. And when I do, I leave the junction and I go through a resistor to get to another place where there's a straight line. So that's what I'm going to do. I'm going to draw on this side. And then I get another straight line. Now on the other side, my green line goes through two resistors until it comes back to that straight line. Now I'm back to my straight line. It looks like my green line goes all the way back to the battery. So, some of you will see that the circuit on the right makes more sense to you than the circuit on the left. Helps you identify things that are in series and things that are in parallel. Some of you would have been just fine with the circuit on the left. I'm going to work from the circuit on the right. And we're going to put some values in here. The battery's 15 volts. This resistor is 3 ohms. This resistor is 3 ohms. This resistor is 3 ohms. See a pattern? This resistor is 3 ohms. I don't have to make the resistors all the same size, but in keeping with what is in the lab, where everything is more or less even, I want to have an experience right now where they're the same. Also, I've chosen these numbers so that they work out easy for our work. All right, we ready to actually do the work? Piecewise reduction requires that I take my simple circuit and reduce it. To reduce it, I can only reduce places in my circuit that show me clear series and parallel. There's only one place that has a clear series portion. Those two are in a row. In this process, you are going to be working from the inside elements outwards. So I'm going to take those two, which are the only two that show me something in series or parallel, and I'm going to create a new circuit. A new circuit that is exactly the same as the old one, except I am going to replace those two resistors in series with an equivalent resistance. I'm going to use the rules of series to place a new resistor there that has the same value as what was already there before. Which, by the way, how much resistance would that be? Thank you, 6. I have reduced my circuit down by 1 step. Rescan your circuit, looking for something in series or something in parallel. Do you see either series or parallel? Hopefully we all do. So my next circuit is going to take that parallel element that's here and reduce it to something that is a single resistance. The 3 ohms hasn't changed up there at the top, but I now have 2 resistors that are in parallel. So I have to use my rules for parallel, which are a little more complicated and can bring out a certain group of people that I am definitely looking forward to seeing. Is this 2/9? It's not. You must get common denominators. I'm thinking an appropriate set of common denominators might be 2/6 and 1/6. And then I must add them together to get 3/6, which of course means that my resistance is 2 ohms, right? We don't want to make the mistake and forget to invert the answer. Now I get to keep erasing, but your paper's probably looking messy. I hope you're keeping notes on the side about what it means to do piecewise reduction, breaking your circuit down one little step at a time. Still not done yet though. You're not done until you have a single resistance that represents the entire circuit. But this one's going to be easy. I think all of us know that those two are in series. So this is my final step, which is going to give me 5 ohms as the resistance of the entire circuit. All right. Once you've reduced your circuit down and you've got it to the simplest resistance, please note any mistake made early cannot be repaired. You'll know you've made a mistake because when you start checking your work, it won't check out. But mistakes made reducing your circuit are hard to recover from because they're so early in the process. So be careful with your math, is what I'm trying to say. But now we apply Ohm's law. There are 15 volts, 5 ohms. We know that at this point, there must be 3 amps pulled from the battery. So, I'm going to go from here back to here. Piecewise reduction, we now work backwards, taking with us the appropriate voltage or current back to the situation we were in before. In this case, my resistor is going back to a system that was in series. So I take with me the current and apply it to each element that's in series. Apply the current to series. Now, I use Ohm's law again to find voltage. This process is just replicated over and over again using some version of Ohm's law. We used I equals V over R before, but now I need to find the voltage, so I'm going to use I times R. At the top, 3 times 3, 9 volts. Bottom, 2 times 3, 6 volts. I'm done. I have the voltage and current for every element in my circuit. I should check my work. 9 plus 6 does equal 15. When you check your work, check between steps like this. Whatever you just solved for should equal what was there before. There were 15 volts there before, there should be 15 volts there now. Now I'm going to step back, but before I do you notice that this resistor is the same resistor as the one from the very beginning? That if I step back, it's the same 3 ohms there as is there. So I'm just going to skip the middleman and write 9 volts, 3 amps. I don't have to worry about that anymore. That resistor is done. Unfortunately, this one's not. And I'm going back to a system that's in parallel. So what do I take back when I go to parallel? Do I take voltage or do I take current? It's got to be the opposite of the last one, so it's voltage. When you go back to a parallel element, you take the voltage and apply it to each, not the current. So parallel gets voltage. So 6 volts here, 6 volts here. Use Ohm's law, 6 divided by 3, 2 amps. 6 divided by 6, 1 amp. 2 amps plus 1 amp equals 3 amps. Check your work. How are we feeling? Easy but complicated? Or way easy, not complicated? We'll know Monday morning or Monday afternoon. Now, if you do notice, you'll see that this 6 volts and 2 amps go to that resistor. They're the same resistor. However, that 6 ohm resistor splits into 2 3 ohm resistors. They are in series. You want to leave though. What do I take back? Do I take the current or do I take the voltage? What was that? I heard both words, so that's not good for you guys. Is this element in series or parallel? It's in series. Series gets current. So 1 amp, 1 amp. Now, use my rule for Ohm's law. Voltage equals current times resistance. So I get 3 volts here and 3 volts here. 3 volts plus 3 volts equals 6 volts. It checks. Now, this is the final piece. Every one of these is dissipating power. Voltage times current. So 2 times 6, 12 watts. 3 times 9, 27 watts. 3 times 1, 3 watts. 3 times 1, 3 watts. This circuit dissipates 27 plus 12 plus 3 plus 3. That's 45 watts. Why did I do that? Look back at the first reduced circuit, this one right here. 3 amps times 15. How many watts is that? 45 watts. Do you notice how many different ways you can check your work? So,